So let's take a look at this example called hang times of little parachutes. So it turns out sometimes in the summertime here at Austin P, we have this program called SOAR, which stands for, I can't remember, Students Optimizing, Analyzing, and Researching. And some high school students come and they make these little parachutes out of like paper and thread and stuff, and we drop them from various places and record the hang times. So maybe I'll enter these data like so. H for height. Got some heights. Got 1, 2, 3, 4, 5 heights at 5 meters, and 5 observations at 10 meters, and 5 observations at 15 meters, and 5 observations at 20 meters. And I've also got their hang times there recorded into T. So I've got H, heights, and T, the times in seconds. Okay. And the idea, of course, is that they want to, they're trying to actually design a parachute that'll have a long hang time. Let's get a plot of heights, of the hang times versus the heights. Okay, so I can do that like so. Now here's something you can see it's already going to be problematic just from this plot. Our so-called LINE assumptions are not going to be entirely satisfied for doing regression. You can see because it seems to be indicating a non-constant variance, right? As the heights get higher, the variation seems to be getting larger, and that's not an uncommon kind of observation to make when you have such things like when you plot things like weight versus shoe size or weight versus height and so forth. There's just, as you get away from zero here, there's just a lot more freedom to have some of that variation. I can actually test for I mean, of course, maybe what we'd want to do is turn these down sort of on the horizontal there. I guess I could do a linear model, maybe I could call D for data. Maybe I could say is C-bind height with on time, like that. And then there are my data values, and I could do a linear model on first column of D against the second column of D, and actually let's put that in out. Okay, and then I'll get my residuals, store them here, out residual. Okay, and then maybe I'll make a plot of the residuals versus the second column there, my data. Okay. All right. Now you can see what's going on. This is how this problem is, and of course I could standardize those residuals too. I could take standardized residual, take the residuals divided by the standard deviation of the residuals. Okay, and do maybe do Windows and plot the standard deviation of the residuals against the heights there. Okay, and so maybe this one is a potential outlier. It looks like it's out beyond 2 standard deviations, but nonetheless, you see this fanning out kind of behavior there. That's kind of a problem for us. It sort of seems to indicate a potential violation of the constant variance assumption that we need. I can actually do a more sophisticated test for for that if I include this library called cars, C-A-R-S. Now, again, if you don't have the package called cars, you need to go in and first install the package, and you'll need to choose a mirror. I pick something in the United States, maybe Indiana, and then I will look for the package that I need, cars. And by the way, I know that this is a package I need because I've looked up online, how to test for equal variance. There's several tests. There's a Hartley's F max test. If you have equal number of observations in each for each predictor variable and normality is satisfied. There's Bartlett's test, which doesn't require equal number of observations per explanatory variable value, but does require normality. There's something that's a little more robust called Levine's test, and it's in this so-called CARS package. Let me just show you that it is indeed here, C-A-R. There's a cat package. That's not what we want. Oh, it's not CARS. It's just CAR. There it is. Sorry, CAR. So then you click OK and you install it and so forth. But I've already installed it. Then you also have to load it when you need it. You can do that with the library command. Okay, and of course that's giving me an error because again that's a typo there. It shouldn't be cars. It's car, C-A-R. Loading the car package. Okay, and what I want to run is this Levine's test. Levine's test will test for equal variance of responses versus several different categories. You'll notice here that my explanatory variable only took on a finite number of values, right? At 5, 10, 15, and 20. So there were 4 categories or 4 levels of this drop height factor. You can think of it that way. And so Levine's test is going to test. It's going to do a hypothesis test for equal variance. But the nice thing is you don't have to have the normality assumption satisfied, and also you don't even need equal numbers of responses here in these categories. Although we do seem to have them. I'll do Levine's test now, and says that Levine's test is not appropriate for quantitative something or other. What does it say? Explanatory. Oh, okay. So it's confused. It's perfectly appropriate. It just doesn't like that I have numbers down here along the x-axis. So I gotta fix adjust for that. So what I'll do is this is called coding. Okay. Not coding, but coding. Okay, I'll create a new variable called HH. Okay, it's for height, but instead of 5 5s and 5 10s and 5 15s and 5 20s or whatever, I'll have 5 A's and 5 B's and 5 C's and 5 D's. Okay, there are quicker, more sophisticated ways to do this, but you can see the idea here. So now what I'm going to do is run Levine's test on T versus HH, and you'll see it'll work out just fine. Okay, just fine. Okay, now this looks like I'm getting a p-value of about 11 or 12%, and that's not indicating a real cause for alarm here. So it turns out that Levine's test is not all that powerful, especially if they're actually normal. So you can run something called Bartlett's test if indeed those values are coming from normal distributions. It's appropriate to run Bartlett's test. Looks like Bartlett's test is giving a much smaller p-value. What we should probably do, and I'm not going to, but we should probably check for normality of the residuals. But it looks to me like Bartlett's test is indicating, that's almost 10 parts in a million for a p-value, that these are probably not having the same variance. So our assumption is once again violated.